So I'm going to try to quickly talk through an introduction to CIL, an introduction to the CIL's architecture. So this is really going to be useful for the hackathon, and a low-level walkthrough of how we run a CIL algorithm and where the memory lives. So Chris has already said this, but CIL is a mostly Python library for processing and reconstruction of tomographic data. The picture on the right is file type, color-coded by file type, and you can see it's pretty much entirely Python. We've got a little bit of, I can't put my cursor there, there we go. Some C++, but really we rely on our backend to do the heavy lifting. We've got the standard CT pipeline tools here, and a big part is our optimization framework. So this is where our algorithms and this sort of near math modular interface lives. So it's all Apache 2 and actively developed on GitHub. And there we go. Our users, oh, sorry, I'm looking at the wrong screen. I've got lag.
Yeah.
Our users are quite diverse group, from CT experimentalists who don't necessarily want to use the vendor provided software, but still want analytical, fast reconstruction, and the maths community who want to sandbox or benchmark some state-of-the-art optimization methods. And then SERP, who use CIL just for the algorithm backend as a library. These are our CIL modules inside the black box. I'm going to go through in some more detail, but just to quickly cover that we've got some I/O for reading synchrotron and vendor data, some processors that are very X-ray CT specific, some curated recon modules for, again, fast sort of for the X-ray CT users that don't want to delve into the maths of the optimization framework, and some utilities for visualization and example data sets. So zooming in on the black box, we have our framework, and this is really where the bulk of the X-ray side of things live. This defines our data types and the functionality they implement. On the right, I've listed our three main plugins, so equivalent to Cinnabee using Stir and Gadatron to do for their backends. We have Astra and Tegra, which provide a set of forward and back projectors, and the regularization toolkit, which is some optimized functions, both on CPU and GPU implementations. The optimization module is where our algorithms live. So we have sort of some templated, or lots of templated algorithms that the users can put in different functions for their data fidelity or their regularization. We define functions as sort of the things that map from one space to a real number, so TV or least squares, and operators being the thing that maps between two spaces. So these are the direct and adjoint, the physics model or projection operators are examples. Our framework, this is how most of our data is defined in these data containers, which are just NumPy arrays, but with dimension labels, which makes it sort of, it means we can't just subclass directly from NumPy arrays, but we might be moving in that direction. We've implemented methods on our data containers that are lots of pixel-wise operations, lots of them implemented in NumPy, but not all. Some of these have C++ implementations and are interfaced via C types. And from here, the children class are the acquisition data and image data. And I think these are going to be really the focus of our work on the hackathon. Again, there's some methods implemented that mean you can't just slice the data and keep the geometry consistent for CT. In terms of the optimization framework, I've got some code on the right that just shows how to create an algorithm and run it in CIL. So we set up a least squares function. We add a projection operator. So you can't see the full example, but this was from Astra. Pass your data. And here we've got the regularization function. So this is from the regularization toolkit, set to running CUDA on the GPU. We pass it to Vista and we run one iteration. So it's got quite a near maths interface that lets you plug and play with different functions and operators. All of our algorithms create the memory buffers that are needed when you set them up. And some of them use quite a lot of memory. Over projection operators, really for CT, this is, I'm less sure about PET and MR, but for CT, this is where the bulk of the work in an iteration is done. This forward and back projection are really costly. We use Tegra and Astra to, well, we offload our computation to Tegra and Astra that do the forward and back projections, and they're really efficient on the GPU because the computational complexity of the transfer to the GPU scales by n to the 2, whereas the image update scales with n to the 3. So it's certainly worth moving this to the GPU and doing the work. In the CIL Python level, we have a projection operator object, which converts the CIL geometry to whichever backend you've requested. And it's only when you call direct in a join, we pass the NumPy array around via Python wrappers to both of them. And they handle the interactions with CUDA. The other plugin we rely on is the regularization toolkit. So this is similar. It's C++. We've got C++ implemented functions on GPU. Here, the transfer to the GPU scales by n to the 3, as does sort of the most complex step in TV is the gradient step, I guess. So which scales by order of n to the 3. But because it's the internal algorithm that's run in the proximal step, we run it many hundreds of times. So it's got a big multiplier, which again makes it worth doing the compute on the GPU. And just for context, I've included some sort of standard CT dataset sizes. They're going bigger than here. 4K is becoming more usual, but that's not feasible with iterative reconstruction at the moment. And as you can see, you quickly get out of the realm where you can leave everything on the GPU. You can't even have your data and your image on the GPU when you're doing the update. It has to be cleverly chunked up. For cone beam CT, you can't just pull out different layers or slabs of data from the grid. There's not a one-to-one relationship between rows on the detector and rows in your volume. So it's got to be handled well. And as Astra and Tegra implement it, I'm sure there's asynchronous transfer and computation going on as well to make this really well implemented. So I'm not sure how well this example will work, but these are the same lines of code I showed you before. And I've tried to run through step by step, running one update of Vista, what's happening between CIL and the backends. So here, Y is a memory buffer the size of your data, X is a memory buffer the size of your image. As you can see, you create the data. This is allocated in NumPy. When you set up Vista, you allocate 4 image buffers in NumPy. And then the first step of the update, you do a forward projection of your solution. Again, we allocate a data container to hold the result. Through our wrappers, we pass pointers to X and Y and leave Astra or Tegra to compute the forward projection. And this is, I've said potentially in slabs, but pretty much always for any real size data set on a normal GPU, this is going to be done in slabs and then have the result passed back to CIL. Then there's an algebraic step. This is, I think, is just doing a subtraction between the forward projection and your data before you go back to the adjoin and again pass the reference to the data and the result, compute the back projection before coming back to NumPy and doing a very small amount of algebra. So these 4 steps are gradient descent, but we've got Vista, so now we take the proximal of TV, which again goes from NumPy, passes through now D-types wrappers to the regularization toolkit, and here this internal algorithm, so in this case FGP-TV, is either run in its entirety on the CPU or GPU. There's no clever slabbing or curating of the data. So this needs quite a lot of memory once the data gets large. Then we come back to NumPy for one final algebraic step. And so this is sort of interesting that we can't do everything on the GPU, but it matters where the data is and where we're doing the compute. And these algebraic steps, it's not worth transferring anything to the GPU if they're in NumPy, because they're very small. You wouldn't make up the transfer cost. So for the hackathon and PyTorch interoperability, I think this is open to discussion. Hopefully we'll make some progress in the week, but I think we want to focus on extending our data containers to wrap PyTorch tensors and not just NumPy arrays. And maybe these are CPU PyTorch tensors initially, so we can keep the same model within our algorithms data transfers. We want to look at PyTorch projection operators, so that's seeing what's happening with Astra and Tegra and what we can already use and what we can support to make this efficient data handling. And look at PyTorch wrappers to the regularization toolkit. We've got some open discussions and PRs in place already, but it would be good to have some momentum on them. So this is just the hackathon plan from the website. I'll jump through there and say we've got quite a few CIL developers. Not everyone's on CIL all the time. We've got other software packages and other scientific projects, but the 4 of us that will be at the hackathon for the week are in pink. And very quickly, we're funded by CCPI and ALC. As Chris briefly alluded to, the CCPI network's really strong. They pay for some software engineering, the UK network events, as well as exchange of information and training. And this work is directly from the current grant we have to October 2026. So this is from, this work is entirely funded by CCPI, and I guess this hackathon is partially funded by them. So we've got some long-term funding to get this developed. And I think that's everything.